Alright, the last of our topics for this chapter is tying it all together. And the way that we do that is a reaction called the Robinson Annulation. A piece of mechanistic artwork, if ever there was one. So, your book doesn't cover it. I find that more than slightly depressing. It is, to my mind, insulting that they don't expect you to look at that and be able to understand it, because all it is the same mechanisms plus one resonance structure. So we, of course, are going to go after it. I would love to show you multiple slides on it, but they don't have any. This is it. This is all they think you need to see. We'll take what they said, then we'll draw our way through it, because it's extremely good practice in making sure you understand what's going on with the other reactions in the chapter, since this is just two of them back to back. It's a Michael addition followed by an aldol. That's it. There's a little bit of weirdness in the middle, equilibrating one enolate to another, but that's not hard. We did that in other parts of the chapter. So, the idea, though, is that this is a way of forming a six-membered ring. So, we're looking at this part right here. These bonds are still here. So that's this. What I've got that's new is now I've formed a six-membered ring off the side of the original one. The reason that's useful, and particularly this example is called the Weiland mixture or ketone, I probably mispronounced that badly, is that it gives us a way to making complicated ring structures. This particular one is very useful for making synthetic steroids, a big part of everyone's life. So let's have a look. So here we are. We have our diketone. It needs to be stabilized here because we don't want to have any mixtures going on, but again, as with things earlier in the chapter, we have ways to play with that if we need to. First, we form an enolate. Mechanistically, again, not surprising. I'm going to draw this with the anions on the carbon to make our life a little simpler. Just so we can see it clearly, what's going on without having to draw any additional resonance structures. So this is enolate number 1. Probably guess if I'm numbering them, there's going to be quite a few. Well, not that many. But the point is, just to keep things straight so we can refer to them again later. So after we have that, the other piece of the puzzle is methyl vinyl ketone, which is an alkene on one side of a ketone and a methyl group on the other. We have other options, but this is a simple example for now. So this is our conjugate addition. So here is the Michael addition step. And again, all of these are equilibria. Our other byproduct here from that deprotonation is water. And we have that in solution anyway. Anytime you have hydroxide, basically almost guarantees that the solvent is water. But just so we're clear, there's water here, and we just formed more of it in case it wasn't. All right, so I have a methyl group that was still on that attachment carbon here. And I have now 1, 2, 3, 4 carbons off that. And at the very end, there's a double bond. This is my new enolate. So our problem here is that that enolate has plenty of places to go to an aldol, but they're too short. So if I try to use that to close down a ring, that's 1, 2, 3, it would only be a 4-membered ring. So that's not likely to happen. So what we have going on next is we're going to kill off the enolate. It's going to end up getting protonated. Now, this is a uniquely strange case, this reaction. It's part of the reason why I think it's worth drawing through it. Is it's one case where equilibration is not leading us to a better enolate. At all. So, enolate 2 really had nowhere to go. And this is in water, so I can protonate it if I need to. Then, we have the base again. This is still catalytic base, just like the aldol. I don't need very much sodium hydroxide to get this to work. Only now, we're going to deprotonate the outside. This is faster. And more to the point, though, it's productive. That enolate has somewhere to go once we form it. So, I have this, and I have, this is now enolate number 3. Well, if I'd look at this now, that's carbon 1, 2, 3, 4, 5, and 6. If that were to undergo the aldol, then I get a six-membered ring, which of course was, as I mentioned, in the only thing your book actually did show, is the point of this, is we get a six-membered ring out of it. Notice that this is a less favorable enolate, number 3. So left to its own devices, number 2 would dominate, but number 2 has nowhere to go. It's not productive. This one is. This one has a place to go. It can actually reach to do the aldol. So, it does. Like so. And we have this. Now, hold that thought. We're going to take that over to the next page because we're going to run out of space. All right. So, now, this is still in water, so we're still looking at protonating that, just like we did with the regular aldol. So here we go. We now have our 2 cyclohexanes fused together, each of them with a ketone, this with the leftover alcohol from the aldol, and this. Well, I still have alpha hydrogens here. I'm only going to draw the one because that's all I need. The other one is there, but not necessary for this mechanism. So if I did that, I get yet another enolate. Seems to be a theme here. An endless series of enolates is what this reaction feels like when you first see it. It isn't, but it does feel like that originally. I recognize that. So this is enolate 4. Now it can finish off the aldol condensation by eliminating and displacing the hydroxide. So that's the end of the problem. That gets me here. Forms a double bond here, here, and here. Now, this seems like maybe it's not such a big deal. Obviously, it's complicated. So let's go back for a second to the previous page just so we can see it. So my first enolate was the diketone. My second was the product after a Michael addition. That then has to equilibrate to be able to do anything. That gives me my third. And then to finish off the aldol condensation and displace the hydroxide for the elimination, I have to have a fourth enolate, another deprotonation. Every time I do that deprotonation, I lose a base, and I end up getting it back all along. This is still, the hydroxide is catalytic here. I need very little of it. So, if you think about this, we can kind of see it, that we're going to have 2 six-membered rings with a lot of places we can work with. We have 2 very different carbonyl groups that we could build from. We have a pi bond here. We could build from that separately or use it as part of a conjugate addition. So there's a lot we can do there, relatively straightforward to do so. So here's the point. Just taking a few examples. That methyl group, 2 cyclohexanes, a ketone, and possibly an alkene. Here's testosterone. Bile acids. Dexamethasone is a corticosteroid. Progesterone has that ketone there with the methyl group there. And the only major steroid that doesn't is estrogen or estradiol. It does not have a methyl group there because it's an aromatic ring, so the methyl group has to go. That is a different problem, but still is a similar question. Let's go back. If I wanted to make a structure in the end without a methyl group in it, then I just start without one here. Then I just start without it here. I can get this. It works just fine. So if I needed to make something without that methyl group, I'm golden. I use a slightly different starting material. It's not a problem for me. So my point in showing you this is that if you know how to use it, it opens up the door to being able to make a lot of different things. Now, the problem is not how nature makes the steroids. This isn't how nature makes them. The problem is we need to make drugs to fake out nature. We need anti-testosterone molecules to stop male pattern baldness. We need anti-estrogens to work as birth control pills. We need anti-progestins. We need corticosteroid analogs for anti-inflammatories. So we need to be able to make steroids without them being exactly what nature once made. So we have to have ways of putting most of the pieces in place. This is one big way to do it. It's how it's designed. We now have a pretty good idea of how we can put this all together. Now, one thing though, this is drawn badly. This is the same structure. We're just going to flip it over. I drew it in the way the mechanism works rather than drawing it the way that you might need to be able to draw it to see this a little bit more clearly so we can see what we're looking at. So I have this, this, and this, and then on the other side of the ketone I have this. So this piece is what I'm talking about in the steroids that you could see with the methyl group in the six-membered ring with the ketone or with an alcohol for things like estrogen. And then this is going to give me a way to put the other two rings in place. Off that I can do enolate stuff here. I can do direct nucleophilic addition here. So it'll be a little bit of work, but the point is I can build off the other steroid rings from this existing two-ring structure. I could, and people have actually, done the same thing from here. So if I start with a different diketone to begin with, I can end up with a 6,5 fused structure like this. And that gives me options that I didn't have before because that's the other side of it. So that gives me options to make this piece. The two left-handed rings up here where I have that methyl group and I have something here. In a lot of cases, there's a ketone there. So I have a ketone there, a 5-membered ring, a 6-membered ring, and then I can build off that. So, same idea. I can build off my other two 6-membered rings from here. And I'm in steroid land. The steroid core ring structures are 6, 6, 6, and a 5. So that's the generic steroid. And then depending on what's where, it's either a hormonal steroid or a glucocorticoid.